Assuming we were conducting a hypothesis test by taking a sample from a normal distribution to test the population mean. If it's a one-tailed test at a 5% significance level, well, in previous tutorials, we found it helpful to draw a graph which represents the sampling distribution of sample means x bar. And assuming that it was a lower tail test, we came to the conclusion about whether to accept or reject the null by comparing the p-value with the significance level represented by this red shaded region. If the p-value was less than 5%, then we would reject the null hypothesis.
And this is why we call this area
the rejection region. If the p-value for the lower tail was more than 5%, then we would accept the null hypothesis. And that's why this region is called the acceptance region.
However, there is another way of deciding whether to accept or reject the null hypothesis. Notice that this 5% significance level corresponds to or maps to a certain value in the sampling distribution, which is on this horizontal line. Let's call this value x bar sub 1.
Now, relative to this significance level of 5%, what do you think would be the p-value of any observed value that is larger than x bar sub 1? Will it be smaller than 5% or larger than 5%?
Well, assuming the observed value was, say, x bar sub 2, which was here, hopefully you can see by this green shaded area that x bar sub 2 would give us a p-value which was greater than 5%, and therefore we would have to accept the null hypothesis. If the observed value happened to be less than x bar sub 1, say it was x bar sub 3, hopefully you can see by this purple shaded region that x bar sub 3 would give us a p-value which was less than 5%, and therefore we would have to reject the null hypothesis. The special name for this value x bar sub 1 is called the critical value, which you can find by working out the equivalent value in the sampling distribution to the significance level that you're given in the question based off of the tail of the test. And it's a very important value because it's the cutting edge between whether to accept or reject the null hypothesis, depending on whether an observed value is greater than or less than this critical value. In this case, any observed value less than the critical value would lead to us rejecting the null hypothesis.
And that's why the special name for this region is called the critical region. It's not the same as the critical value, but represents the set of values for which, if we find any of those values in the sample, then we would reject the null hypothesis.
And any value which is greater than x bar sub 1 would lead to us accepting the null. So this is how we conduct hypothesis testing using critical values. Instead of comparing the p-value with the significance level, we compare the observed value from the sample
with the critical region that we can define after finding the critical value.
Or in other words, instead of comparing percentages illustrated by areas, we're comparing numbers illustrated on the number line,
which represents the sampling distribution.
Let's look at the general idea behind this mathematically. Now, given that this is a lower tail test, the way that we've previously calculated the p-value of an observed value is by working out the probability of finding that observed value or something less. Now, if we were to find that the probability of getting x bar sub 1 or less is exactly equal to 0.05 or 5%, the significance level, then we can say that the critical value is equal to x bar sub 1.
The equivalent value in the number line that corresponds to a 5% significance level on the lower tail.
So if we let a be some value which is less than or equal to the critical value x bar sub 1, which could be any value along this purple line, then the probability of getting values less than or equal to A must be less than or equal to 0.05, as we established earlier. And this would cause us to reject the null hypothesis,
because it would lie in the rejection region. The critical region in this case, illustrated by this region, would be defined as the set of observed values that are less than or equal to x bar sub 1, the critical value.
If we were conducting a one-tail test on the upper tail, well, to find the critical value, we would need to find the value where the probability of getting that value or anything more would be exactly equal to 0.05. So assuming we had this scenario where the probability of getting observed values greater than or equal to, say, x bar sub 2 is equal to 0.05, well then that means that the critical value must be x bar sub 2, which we can illustrate here on the diagram. So if we let A be some value which is greater than x bar sub 2, which could be any value along this purple line, well then the probability of getting observed values greater than or equal to A
must be less than or equal to 0.05.
Remember, if you go along this line and you work out the equivalent p-values, you'll see that it starts to get smaller and smaller. And therefore, we would reject the null.
So based on this and the critical value we've just found, we can say that the critical region, illustrated by this region, can be defined as the set of observed values greater than or equal to x bar sub 2, the critical value in this case.
Okay, let's now look at the same ideas for a two-tailed test. For a two-tailed test, we have a similar approach. However, for two-tailed tests,
we need to consider the critical values and the critical regions for both tails.
And remember that for each tail, we are taking half of the significance level as we did for the p-values. So, starting with the lower tail, if there is a value, say x bar sub 3, such that the p-value is exactly equal to 0.025, or half of the significance level, 2.5%, then the critical value would be equal to x bar sub 3, which would correspond to this position on the diagram.
Now if we let a sub 1 be some value which is less than or equal to x bar sub 3, which could be any value along this purple line, then the probability of getting observed values less than or equal to a sub 1 must be less than or equal to 0.025, and this would cause us to reject the null hypothesis. And so the critical region would be defined as the set of observed values that are less than or equal to x bar sub 3, the critical value on the lower tail.
For the upper tail, we would need to do the same in order to find the upper critical value. So if there is some value x bar sub 4, such that the p-value is exactly equal to 0.025, then the critical value would be equal to x bar sub 4, which corresponds to this position on the diagram.
Notice the difference in the direction of the inequalities when calculating the p-values for the upper and lower tail. And you need to be aware of this for the correct calculation of the critical values.
So if we let a sub 2 be some value greater than or equal to x bar sub 4, which could be any value along this purple line, then the probability of observed values greater than or equal to a sub 2
must be less than or equal to 0.025.
And therefore we would reject the null hypothesis. And so the critical region in this case would be the set of observed values that are greater than or equal to x bar sub 4. Okay? So for a two-tailed test, we need to consider both tails, and remember that we'll have to work out two critical values and subsequently
two sets of disjoint critical regions.
Okay?
So far we've looked at the general idea behind finding critical values and critical regions. In the next tutorial, I'm going to be showing you examples where we calculate these critical values
and based off of the observed value found from the sample,
work out whether to accept or reject the null using critical values.
Stay tuned for the next tutorial. If you like this video, please give us a thumbs up, leave your comments down below, and subscribe to this channel so you'll be the first to know when we release our next videos.